In this video, we will do an implicit differentiation example involving demand, price, and revenue. So we're going to apply implicit differentiation to a demand, price, revenue type problem. So the question says price and demand are related by the equation ln of qp plus 4 equals negative 6 over p. Okay, so this is an implicit formula because I don't have one of the variables isolated in terms of the other one. So part A asks to find the rate of change of demand with respect to price if the price is $3, and interpret your answer. Okay, so first I want you to just pause the video for about 1 minute and see if you can determine what is this question actually wanting us to find. So 4, 3, 2, 1, pause the video. Pause the video for 1 minute and see if you can determine what does this question want us to find. Like, is it a certain derivative? Is it a certain value of a function at a certain point? What is it exactly? All right, so hopefully you've paused the video and thought about that. So there are two things that I want to comment on here. So when a question talks about finding the rate of change, we know about two types of rate of change. We know about average rate of change and instantaneous rate of change. But this problem doesn't specify which one it is. If it doesn't specify whether it's average rate of change, AROC, or instantaneous rate of change, IROC, it means instantaneous rate of change. So if a question just says, find the rate of change, it means find the instantaneous rate of change. And the instantaneous rate of change, remember, is the derivative. So what this wants us to find, and this goes back to my first question that we paused the video to try to answer, is it wants us to find the derivative of what? It says find the rate of change of demand, so it's going to be the derivative of demand with respect to price, so that means with respect to the variable p for price. So it wants us to find that derivative when, so remember the vertical line means now plug in a certain value, plug in p equals 3. Plug in when the price is 3. Okay, so let's see if we can find that derivative, and then plug 3 in for p. Alright, so I've gone just up to the top of the page, so I give myself some more room to write, and I've copied down the original equation here. And let's remember, we want dq dp at p equals 3. P equals $3. Okay, so we need to do implicit differentiation for this, because this formula is defined implicitly. I don't have one of the variables isolated in terms of the others. So let's take dp of both sides. Because I want to get dq dp, and to get dq dp, I'm going to need to take the derivative with respect to p of both sides. All right, so we'll have ddp of ln of qp plus 4, so the derivative of the left, equals ddp of the right. To take the derivative of the right, it's going to be helpful to rewrite it as minus 6p to the negative 1. So in other words, what I've done is I've brought that p up to the numerator. Okay, because now I'm going to get to use the power rule. All right, so on the left, I have ln of some stuff. So I need chain rule for this. So on the left, I need chain rule. Because I don't just have ln of p, I have ln of some stuff. And chain rule says, we'll first take the derivative of the outside, the ln, and I'll get 1 over the stuff that's inside, qp plus 4. But then chain rule says, well, multiply that by the derivative of the inside. So the inside is qp plus 4. Okay, so that's how we take the derivative of ln of stuff using the chain rule. And on the right-hand side, that one's not too bad. It's just power rule. Bring the negative 1 down. It'll give this positive 6. And then I subtract 1 from the power and get p to the negative 2. All right, so we still got to take this derivative of qp plus 4 now. So I have 1 over qp plus 4 in front. And I have to take the derivative of qp plus 4. So let me give myself some room for this. So when I take the derivative of QP first, that's going to involve the product rule. So I do the first function times the derivative of the second. So times the derivative of the second, derivative of P, plus the second times the derivative of the first, ddP of Q. All right, so that's my derivative of QP, but then I have to add the derivative of 4 to that. 4 is a constant, so its derivative is 0. So nice. All right, so on the right-hand side, we still have 6p to the negative 2. All right, so let's finish these two derivatives that showed up in product rule now. We have 1 over qp plus 4. And in green now, I have q times. So the derivative of p is just 1. It's just 1. Because I'm taking ddp, that means I'm thinking of p as my variable. So this is just like a normal derivative. Okay, and then we have plus p times, now I need to take ddp of q. So for this one, we have implicit differentiation going on. So remember, the way that we think about this is ddp of, and then with q, we're thinking of q as a function of p. So we're thinking of q in this way, as being some function of p. And we've seen before now a couple times that this derivative is just dq dp. That's how I write it. That's the derivative of q with respect to the variable p. Okay, so that is dq dp. Let's close that bracket. And this equals 6p to the negative 2 on the other side. All right, so now we have taken the derivative successfully on both sides. Once we do that, this is typically the point where we plug in our point. So the point, remember, was p equals 3. Let's take that and let's plug it in. So now let's plug in p equals 3. Remember, we wait until after we take the derivative to plug in the point. All right, so doing that, we get 1 over 3q plus 4. And then parentheses here, we get q plus, plugging in 3 times dq dp equals, on the other side, I'm going to get 6 over p squared, which is 6 over 3 squared, 6 over 9, which simplifies to 2 over 3. All right, so one thing that makes this problem different from the previous examples that we've done on implicit differentiation is, before, when we took our derivative, we knew the values for both of the variables. So we were able to plug in for both of them. But in this problem, it only tells us the value for one of the variables, for what p is. But we don't know what q is. So we need to figure it out. Okay, so pause the video one more time for about 1 minute and think about, how do we figure out what q is, what the value of q would be at the point when p is 3. 4, 3, 2, 1, pause the video. Pause the video and think about, well, how do we figure out q now? All right, so hopefully you've done that. Hopefully you've paused the video. Let's talk about it together. So the way we are going to do that, the way we're going to get the value of q is, since I know p, I can use my original equation and plug in my p value into the original equation and then solve for q there. All right, if we do that, let's write this down. Let's find q using the original equation. All right, so that gives us ln. So remember, the original equation is qp plus 4 equals negative 6 over p. And at this point, now we are going to plug in our value for p, which was 3. So doing that, we get ln of 3q plus 4 on the left. On the right, we'll get negative 6 over 3, which is negative 2. Okay, so we have ln of 3q plus 4 equals negative 2. Okay, so this is just a log equation, and we reviewed these back in the first 2 weeks. We can transform this to exponential form. So the base of ln is e. So this becomes e to the negative 2 equals the stuff that's inside of the log, 3q plus 4. So remember, when you convert from log form to exponential form, the exponential is the inverse of the log function. So we're switching the roles of the input, which now becomes the output of the exponential, and the output of the log, negative 2, becomes the input of the exponential. All right, so now let's just continue to isolate. So if I subtract 4, we get e to the negative 2 minus 4 equals 3q. And dividing by 3, we get q equals e to the negative 2 minus 4 over 3. Okay, all right, so I'm going to put this in a little thought bubble. So this is how we find q. So I can use my original equation. All right, so now that we have that, now that we have that value of q, we are ready to take that and plug it in here. Because that's where we were after we had taken the derivative and we had plugged in our value of p. Now we want to plug in our value of q into this equation. So doing that, we get 1 over 3 times q, and q is e to the negative 2 minus 4 over 3, plus 4, and then bracket another q, so e to the negative 2 minus 4 over 3, plus 3 times dq dp equals the 2/3 that we have on the other side. All right, so let me zoom into this so we can work with it. Let's zoom into this. All right, so looking at this, we have some simplification going on. So this 3 will cancel that 3 at the bottom. And after that happens, we have a little bit more cancellation that happens. The minus 4s, the negative 4 cancels with the positive 4. Okay, so those cancel. So we end up with 1 over e to the negative 2 on this left-hand side, in front of the bracket. And then that's multiplying within the bracket e to the negative 2 minus 4 over 3 plus 3 times dq dp equals 2/3. Okay, so we just did some simplification there, some cancellation. Now let's multiply both sides by e to the negative 2 to get rid of this fraction outside the bracket. So I'll do the same thing on the right. So doing that, we end up with e to the negative 2 minus 4 over 3 plus 3 dq dp equals 2e to the negative 2 over 3. All right, so now let's subtract the fraction, this e to the negative 2 minus 4 over 3 to the right. We'll get 3 dq dp equals 2e to the negative 2 over 3 minus e to the negative 2 minus 4 over 3. Okay, and then we could subtract these. So when I subtract these fractions, because they have the same denominator, 2e to the negative 2 minus e to the negative 2 is e to the negative 2. And then when you apply this negative sign to the negative 4, remember, we're going to have to sort of distribute. We're going to have to distribute the negative sign. So we'll get plus 4 over 3. Okay, so now to get the dq dp isolated, we just need to multiply both sides by 1/3. So I'll multiply this side by 1/3. And if I do that, I have to multiply this side by 1/3. Okay, let's actually just do that on the next line. So if we do that, we'll end up with dq dp on the left by itself. And when you multiply the right by 1/3, you'll get e to the negative 2 plus 4 over 9. Because you get 3 times 3 in the denominator, which is 9. And that is my derivative. That is dq dp at the point where p equals 3, like it wanted. So this question also said, well, once we have that, interpret our answer. So remember, these derivatives, when we plug in a point, tells us the approximate change in whatever function we're talking about. In this case, the approximate change in the function q, in demand. Okay, so the interpretation is if we increase the value of P by 1 unit from $3 to $4, so that would be increasing the unit of P by 1, we approximate that demand, our function, this number right here is a positive number. E to the negative 2 is positive and everything else is positive. So because of that, we are going to approximate that the demand increases. It's going to go up. It's going to increase by e to the negative 2 plus 4 over 9. And that is my interpretation. So it's important to keep in mind, sorry about that, I kind of slashed through that 9 a little bit, but that is my interpretation. It's important to keep in mind that this derivative just gives us an approximation on how much the demand changes. We don't know for sure that this is exactly how much the demand will change when we raise the price by $1. All right, so let's do part B of this example. So now let's find the rate of change of the revenue with respect to price if the price is $3, and interpret our answer here. All right, so this one I want to leave for you to try, and I want to give you more time, so hopefully you can try this whole thing. So pause the video this time for 3 to 4 minutes to try this problem. 4, 3, 2, 1, pause the video. Pause the video for 3 to 4 minutes to try this question. So the examples in this video are definitely a step up in difficulty from the examples that we've seen before this. Their applications, the functions in general are a little bit more complicated. The numbers that we get when we plug in are a little bit more complicated. So because of that, it's a really good practice problem. It's really good to practice a question of this difficulty level and see how well you understand the ideas. All right, so hopefully you've done that. Hopefully you've tried it. Let's go ahead and talk about it now. So the question here says, to find the rate of change of the revenue with respect to the price. So it doesn't specify average or instantaneous, so that means instantaneous. That's what I said at the beginning of the video as well. So an instantaneous rate of change is a derivative. So this wants us to find the derivative of revenue with respect to price, so it's dr dp, at the point when p is 3. All right, so now I need to write down an equation for revenue. So remember, revenue is P times Q. So this problem didn't give me this equation for revenue, but this is something that we've seen a bunch of times. So we know this equation. Okay, so the problem is kind of trusting that, oh, we know this equation, so we know how to write it down, and now let's try to use it. Okay, so we have this equation, and to find dr dp, I'm going to have to take ddp of both sides. So let's take ddp of the left and ddp of the right of p times q. And this time, because now we've done a few of these implicit differentiation questions, now I'm going to start to just do these derivatives. So even though for ddp of r, technically this means we're thinking of r as being a function of p, we're thinking of this as ddp of r of p. And we do that anytime the variables are different. So the p on the bottom of this is different from the r that I see within this function. Whenever I see that, I need to think about this variable, the r, as being a function of that variable that I'm taking the derivative with respect to, price. Okay, so this derivative is just dr dp. dr dp, that's how we write that. And I can see that up here from this notation. But now more and more, I'm just going to start to not even write this stuff and just go and say, oh, that's dr dp. So on the right-hand side, we need product rule for this derivative. I'll get the first function, p, times the derivative of the second. So the derivative of the second is just dq dp. So I'm doing more of just starting to say what the derivative is rather than writing it in this form. Okay, so plus the second function, which is q, times the derivative of the first, and the derivative of the first is 1. So for the derivative of p, I do not need to write it in this like dq/dp or this dr/dp form, because the variables are the same. The p is the same as the p on the bottom, so that means it's just an ordinary derivative. No implicit differentiation needed for the derivative of p. All right, so we have dr/dp equals, and now let's plug in the stuff that we know. Well, the price was given to us, that's 3. dq/dp, well, we just figured that out in the last problem. Okay, so we actually needed our answer to the last problem to plug in for dq/dp. It is e to the negative 2 plus 4 over 9. And then plus the value of q. Well, q we also know from part A. So we know from A. And the value of q was actually e to the negative 2 minus 4 over 3. Okay, and this is times 1. All right, so continuing on to the next page, we get dr/dp equals, so the 3 and the 9 will cancel a little bit, and I'll get e to the negative 2 plus 4 divided by 3, and then plus e to the negative 2 minus 4 over 3, because multiplying by 1 just keeps that fraction the same. So we have the common denominator, so we can just add these. dr/dp equals, so we have e to the negative 2 plus e to the negative 2. That's 2e to the negative 2. And then 4 added to negative 4 is 0. Okay, and then all over that 3 in the denominator. And that is dr/dp right there. Okay, but it wants us to interpret this answer as well. So the interpretation should be really similar to our interpretation for that last question. So if price, because that's what we were taking the derivative with respect to, price, increases by 1 unit. So if it increases from $3 to $4, we approximate the change in our function in revenue will be this value that we see here, 2e to the negative 2 over 3. And what are the units here? So the units of revenue in this question were dollars. And notice that since this number is positive, which means that the revenue increases. At least that's what we approximate, which means we approximate that the revenue increases. Okay, and then the fact that we wrote the units here for this question reminds me that I should go back and write my units for part A as well. So going back to my interpretation for part A, we said that the demand increases by this fractional quantity. So the units there would just be this many items. This problem didn't specify what the thing was, so I'm just going to say it's that number of items, whatever my item happens to be. So finally, in terms of our goals, we have done our final goal for this section. We did an example of implicit differentiation to one of our applications involving price, demand, and revenue.